Welcome back. This is Analog Electronic Circuits and today is lecture 23 and we were discussing op amps and OTAs in the last class. So, we are going to continue with the same, the op amps and the OTAs, and we are also going to look at how negative feedback is going to be used with these op amps and OTAs. That is pretty much the topic for today's lecture. Okay. So, in the last class we were talking about possibly your favorite op amp circuit. So, one was this, and the other was a variation of that. Okay. And the analysis of these circuits is very straightforward. All you have to remember is that if you have drawn the circuit right, then the voltage at minus terminal is going to be equal, more or less equal, almost equal to the voltage at the plus terminal, okay, which means that the voltage at the minus terminal in this particular circuit is 0. In the other circuit, once again the voltage at the minus terminal is more or less going to be equal to the voltage at the plus terminal, which means in this circuit the voltage is V in. All right. So, this is all that you have to remember. There is one more thing that you need to remember, that is the current going into the plus and minus terminals is always 0. So, remember this is the gate, I mean the op amp, inside the op amp there are MOSFETs and these are gates of the MOSFETs. Okay. So, the current going into the gate is 0, which means that the current going into the minus terminal is 0, the plus terminal is 0. So, whatever this current is, by the way, what is this current? This side is V in, the other side is 0. So, this current is V in by R 1 naturally. All of this current is forced to go the other way, because no current can go into the minus terminal, which means that the drop across the R 2 resistor is going to be the current times R 2, which means that the drop across the R 2 resistor is going to be V in times R 2 by R 1. Okay. You start from 0. So, the potential on the plus side is 0, that means the potential on the minus side is going to be minus V in times R 2 by R 1, and that is going to be your V out, and automatically that means that V out by V in equal to minus R 2 by R 1. So, this is the standard analysis, this is the shortcut analysis that you need to know, because these circuits are going to come often and you need, these are all very famous circuits which are favorites of a lot of people. In the second circuit, what happens? This is V in, so the other terminal is V in, and therefore, the current over here is V in by R 1. And clearly, this current has to come through R 2, it has no other way, right, because the current going into the minus terminal is 0. So, that current has no other way, it has to come through R 2, which means the drop across R 2 is V in by R 1 times R 2. Okay. So, you start from V in, that is the voltage at the minus terminal. So, the voltage at the plus terminal of R 2 is going to be V in by R 2 by R 1 more than V in, which means V out is going to be equal to V in plus V in times R 2 by R 1. You can take V in common. Okay, and that is your V out by V in. All right. So, this is the standard way of analyzing this. Now, we have one important issue over here. This is what we were discussing in the last class. The issue that we have is that the op amp that we made is not really an op amp. What we made is an operational transconductance amplifier. We did not really make an op amp because its output impedance was large. Okay. So, either the output node is a drain, it has got to be a drain of some MOSFET, right. Either it is a cascode drain or it is an ordinary drain, whatever it is, the output impedance is somewhat large, and large output impedance automatically means that the circuit is going to behave like a current source. So, instead of a voltage controlled voltage source, which the op amp should be, what we have unfortunately made is a voltage controlled current source. And the question that I was trying to answer is that, is this going to affect anything? If I place a voltage controlled current source, by the way it is drawn like a trapezium, not a triangle, this voltage controlled current source. Okay. If I make the same circuit with an OTA instead of an op amp, will it work? What is going to happen? All right. So, this was what we were thinking about in the last class. Now, first things first, what is the current going in to the plus terminal? Oh sorry, this has to be the minus terminal, this has to be the plus terminal. What is the current going into the minus terminal? This is made up of MOSFETs. So, it has got to be 0, perfect. So, the current going into the minus terminal is nothing but 0, which means whatever is this current, all of that current has to go through R 2. Okay. Now, all that I need to establish is what is this voltage, all right, that is all that I need to establish. Now, what we are going to do is, we are going to do a brief analysis. Okay. Before I discuss what this voltage is, there is one more issue at hand. You saw that I corrected this from plus minus to minus plus, right. Why did I do it? Obviously, the plus minus is a wrong, is a mistake. Okay. What is the mistake over there? Question 1. Question 2, we have been, I am leaving a lot of things unsaid right now, I am trying to ask those questions. So, from the last discussion, from this discussion, one thing that I missed out, or rather did not really tell you, is why are these two voltages more or less equal? That is question 1. Next, is there a problem if I draw plus minus instead of minus plus? Question 3, what is the voltage over here actually in the OTA case, what is the voltage, right, how does it work out? Okay. So, these are my questions right now, and I am going to try to answer these questions, all of these questions with one analysis. So, the idea is this: if you think a long time back towards the first or second class, we had studied the load line. Okay. When we talked about diodes, when we talked about the MOSFET initially, we talked about the load line. Okay. So, we are going to bring the load line back over here, back into the picture and do our analysis. All right. So, the way it works is, let us say, let us call this voltage something, V, what do you want to call it, V x, okay. Since we do not know what it is, let us call it V x, all right. Now, imagine this OTA is not there, let us for once throw it out of the circuit, let us not worry about the presence or absence of this OTA. Okay. Let us not worry what is over here, there is something over there clearly, I do not want to know what it is. Can I write some KCL, KVL? We can write a KCL at this node and that KCL will look like V in by R 1 plus V out, sorry, V in minus V x by R 1 plus V out minus V x by R 2 is equal to 0. In any case, even after you plug the op amp or OTA back in over there, this current is going to be 0. Okay. So, my KCL is still going to be valid with or without the op amp or OTA, whatever it is. All right. Now, this R 1 and R 2, they are just causing extra stress over here. Let us assume R 1 and R 2 are equal without any loss of generality. For now, I am going to assume R 1 and R 2 are equal just for this analysis, because I do not want to write too much. Nothing much is going to change, just that the equations will look a little simpler. The ideas remain exactly the same. If you do not like it, you can keep R 1 and R 2 in your notebook. I am going to remove R 1 and R 2 and call it one general R. Okay. So, if I call it R, then the R can safely cancel out, because on the other side there is 0. Okay. That is why I made it R. And we are going to get V in plus V out equal to 2 times V x, fine. Now, what I am going to do is, V out is an unknown, I do not really know what is going to be V out, all right. V x is the input terminal to my device, let us call this the device. V x is the input terminal to my device, V out is the output terminal of the device. Let us make a graph with x axis as V x and y axis as V out. Okay. So, note clearly the choice of axis. The choice of axis is the input terminal to the device and the output terminal of the device, where my device is the op amp or the OTA, whatever it is. Okay. So, I have an equation over here, V in plus V out is equal to 2 V x, and I would like to plot this equation on this graph, where the x axis is V x and the y axis is V out. What is it going to look like? A straight line, lovely. So, this is going to look like a straight line with a slope of 2, and if V x is 0, V out is going to be minus V in, for example. Okay. So, it is going to cut the x axis, sorry, the y axis, it is going to cut at minus V in. So, whatever V in is, I do not know, right. So, if V in is, let us say plus 0.5, then it is going to cut the y axis at minus 0.5. If V in is plus 1, then this line is going to cut the x axis, sorry, the y axis at minus 1. If V in is 0, then this line is going to cut the y axis at 0. If V in is minus half, it is going to cut it at plus half. If V in is minus 1, then it is going to cut it at plus 1, so on and so forth. Okay, so, you get a family of curves for different values of V in, you can draw different curves, and all of these curves are straight lines which are parallel to each other clearly, right. They are all straight lines with slopes of 2. Okay, my drawing is very bad over here, it looks like it is 45 degrees, it is not 45 degrees, it should be something with a slope of 2. So far so good. What have I done, by the way? I have not done, I have not bothered with the device at all. I have only done one KCL, and this KCL is valid. Whether this device is an op amp or this device is an OTA or there is no device at all, it does not matter. Even if there is no device, it is okay, the KCL is still valid. Fine, not a diode. Diode will not work because it is going to take current. We took this equal to 0, right. So, it should not be that this current starts mattering, right. It should not matter, this current should be 0. So, it should be a device such that that current is 0. Okay. So, op amp, OTA, air, these are valid devices for us right now. All right, so far so good. The next thing that I am going to do is, now we go to the market, purchase the op amp or the OTA, right. You sit at the drawing board, design the OTA, and then you plug it in over here. So, before you plug in, you need to ask the question, what is the characteristics of this OTA? What is the input output characteristics of this OTA? Remember, the input terminal is Vx, the other input terminal is at ground. Okay, so, we do not worry about the other input terminal. The output terminal is V out. All right. Now, the way an op amp or an OTA is going to work is that if the minus terminal is positive, then the output is going to become negative. If the plus terminal is positive, in this case the plus terminal is ground. Okay. If the minus terminal is negative, the output is going to become positive. Okay. So, this is the inverting terminal basically. Then the OTA, you designed the OTA for a large voltage gain, which means that let us say you designed it for a large voltage gain of let us say 10,000. Okay. So, if my input is 1 millivolt, the output is going to, if the input is minus 1 millivolt, the output is going to shoot up, try to shoot up to plus 10 volts. Okay. Now, it depends on what the power supplies of this OTA are. If your power supply is only 2 volts, then of course, you can't shoot the output up to plus 10, it is going to stop at 2 volts. Okay. If the power supply is 1.2, it is going to stop at 1.2. If the power supply is 12 volts, then 10 volts is okay. All right. So, this is what is going to happen. This is the kind of characteristics. So, let me draw it for you. The drawing is going to look somewhat like this, and let us choose a different color to make it clear that what I am drawing is the characteristics of the device. Okay. And the gain of this, that is the slope of this in this transition region, is minus 10,000 in this case. This slope is going to be minus 10,000 in case of this graph that I have drawn, because you have designed the OTA or the op amp, whatever it is, with a gain of 10,000. All right, so far so good. So, you have got these blue lines are because of Kirchhoff, the red curve is because of the device. The circuit has to obey both the blue as well as the red. What is that going to imply? That the output voltage V out, so it implies that it is going to operate at the point of intersection of the two curves, right. So, suppose your V in value is plus 1 volt. If V in value is plus 1 volt, it is going to choose this particular line, let us say, right, which cuts the y axis at minus 1. All right. Now, you have now that you have chosen that line, the point of operation is going to be the intersection point of that line, that blue line, and the red curve, which happens to be this green point. Okay. Now, if I change the input to minus 1 volt, it is going to choose this point. If I choose the input to be 0 volts, there you are. Okay. So, depending on the value of the input, you are going to choose the value of the, you are going to get a value of the output. And clearly, what is going on over here, the one thing that you should be able to see visually over here is that V x is going to be very close to 0. Okay. I mean, it does not matter what is V out, but V x over here has got to be equal to 0, because you are cutting so close to the y axis. Even if it is not 0, it is something very small, okay, because the gain of the op amp is so high, or the OTA. Now, if V x is equal to 0, does it matter if this is an op amp or an OTA? Because this current goes in, no current goes into the OTA, the same current goes out, automatically I have declared the value of V out. It is the same analysis whether it is an op amp or if it is an OTA. All right. So, it should not matter. Right now, it should not matter. You do not really need to make an op amp, and OTA will do just fine. Okay. But take a look at it, be careful, right, think about it before declaring victory. So, it looks as if V x is equal to 0, then the result is the same whether it is an op amp or an OTA. Is the answer, is V x going to be equal to 0 is the question, and that question is answered by this graph, right. If my gain is indeed high, if the gain of the op amp is indeed high, then there is no problem. Okay. Now, there is a slight problem over here. The slight problem is as follows: the gain of the op amp might, the gain of the OTA, not op amp, the gain of the OTA, there is a chance that it is going to reduce because of the circuit. Why is it going to reduce? Remember, the gain of the OTA was the transconductance times the output impedance. Transconductance, you have got something. Output impedance, looking over here, you had some output impedance and you got that output impedance. Transconductance times that output impedance was the gain. But if you look at V out and look at the output impedance, you will have the output impedance of the OTA and also R2, because R2 is right to ground. Okay. So, looking into the output of the OTA, you see some impedance, but you also see R2 in shunt with it. All right. So, the gain of the OTA is going to be now the transconductance times the original output impedance in parallel with R2. Okay. So, there is a chance that the gain of the OTA is going to reduce. All right. So, this is a worry. How worrisome this is depends on how small the value of R2 is. If the value of R2 is very large, then there is no, it is not a problem, because a large resistance is in shunt, nothing much is going to happen. But if the value of R2 is small compared to the output impedance of the original OTA, then we will have a problem. The gain of the OTA is going to reduce, and then what is going to happen? If the gain of the OTA reduces, what happens to my curve? The curve becomes a little weaker, right. Of course, this is a highly exaggerated curve. Instead of a slope of 10,000, you might have a slope of 1000. Okay. Your GM is still large. So, you will still have some gain, and instead of gain of 10,000, maybe your new gain is just 1000. Okay. In which case, this green curve does not look like green, I mean it will still look like the red curve. 1000 slope is still very large. Okay. But in any case, what you are going to see now is that you are slightly off from your answer, slightly off, but you are still more or less over there. You are still going to follow the pattern that Vx is almost equal to 0. Okay. Just that you are a little worse off. How much worse off? We will have to do numerically, quantitatively you will have to assess. Graphically it looks like you are still not that much worse off. Okay. Vx is still something which is very close to 0. Okay. So, this answers a few things. First of all, it answers the question, why are the two terminal voltages more or less equal? This graph should answer that. Number 2, you should be able to understand now why an op amp and OTA are very similar and what is the difference. The op amp has a low output impedance to start with, it is a voltage controlled voltage source. So, the output impedance is very low, it is not doing GM times R out. Okay. In case of an op amp, it is a voltage controlled voltage source with a very low R out. All right. Now, if R out is low, then putting an additional R2 in shunt with it is not going to change anything, it is going to continue remaining low. Okay. So, nothing much is going to happen. All right. The gain is going to remain pretty much the same, because the gain is relying on GM, not on R out. So, GM is very large, R out is very small in case of the op amp. In case of the OTA, GM is all right, GM is a nominal value, R out is very large because it is a current source. All right. So, this is pretty much the difference between the op amp and the OTA. So, 2 questions answered. The third question was that what happens if I interchange the minus and plus terminals? Okay, what happens if I make a mistake? What is going to happen? Are the blue curves going to remain or are they going to change? The blue curve had nothing to do with the device. It was, the blue curves were made when the op amp was thrown out of the picture. So, they will do fine, they will remain exactly where they are, no change in the blue curves. The only change is going to be in the red curve, the curve for the op amp, because now that you have interchanged the minus and plus terminals, right, the polarity of the red curve is going to change. So, instead of the way it is going to start looking the other way. Okay, just the polarity is going to change, because now if Vx is slightly positive, imagine this is plus, this is minus. If Vx now is slightly positive, then V out is going to be positive. Okay, so that is what happened. All right. So, this is the only change that takes place. And then what happens? We have to establish the point of intersection between the blue curve and the device curve. Okay, so, the blue straight line, let us say we pick this straight line, V in let us say 0. Where does it intersect the device curve? Earlier it was intersecting at the origin, now it is still intersecting at the origin, but there are two more points of intersection. So, you have got two new points of intersection. So, this straight line is crossing the device curve at 3 points of intersection, not 1, all right, and this is a disaster. Okay. So, the way it works is, it is either going to be at this top point or it is going to be at the bottom point, it is never going to show up at the center point. All right, it is almost like you have placed a stone on top of a hill, not a stone. You have placed a football on top of a hill and you expect the football to remain right on top of the hill and not roll down any one of the two sides. Okay. And once it is rolled down on one side, it is going to stay there. All right. So, when you make such a circuit, if you happen to interchange the plus and minus terminals, the circuit is going to remain at either the positive supply voltage or the other supply voltage, right, and it is never going to move from there. Notice the gain, the DC operating point gain, the small signal gain at this point of operation is 0. The small signal gain at this point of operation is 0. Okay. So, the op amp has no gain, which means if I now apply a small input signal, nothing is going to change, the output is going to remain exactly where it is. Okay. So, this is totally flat over here. All right. So, this circuit does not work. Basically, if you flip the plus and minus terminals, you will either be stuck at this point or at this point, you will never come in the middle. All right. And that is the reason why the plus and minus terminals are important. Okay. So, you have to draw it correctly. If you do not draw it correctly, if you make a mistake, the circuit does not work. The circuit is not unstable. A lot of people come back and say the circuit is unstable. It is not unstable, it is very stable, right. There is no stability issue over here. The circuit is rock stable. Once the football has rolled down on the other side, it is not even going to bother trying to come back to the other side of the hill. Okay. It is there, it is going to remain there forever now. Okay. So, the circuit is very stable, there is no instability, it is just that there is no gain, and this is not the point, the operating point that you were looking forward to. All right. So, what is the mechanism to make sure that the operating point of the op amp is correct? This mechanism is called negative feedback. All right. So, this is the mechanism by virtue of which the operating point of the op amp was set nicely. For example, in this circuit, so let us now imagine we just have op amps. Okay. I am using right now I am using this triangle and the trapezium interchangeably, okay, and do not worry too much about it, whether it is a triangle or a trapezium right now. So, suppose the input voltage is 0. Now, you can do the analysis of this with the help of these curves, right. You choose the center blue line because the input voltage is 0 and you find that the point of intersection is at the center, and lo and behold everything works out. Okay. That is fine. What we are going to do now, so you already understand that, right, that analysis you already understand. Now, let us think of it in a slightly different way. Let us think of this node Vx. If Vx is a little more than plus, if Vx is a little higher than the plus terminal, then the output terminal of the op amp is going to be a lot lower, okay, because the op amp has, it is at the minus terminal and the op amp has large gain. So, if Vx is slightly higher than what is required, then the output is going to be a lot lower, and what is going to happen when this voltage goes down, it is going to pull down through this resistor. Okay. Now, think of it this way, this side is fixed at ground, all right, this is at Vx. If the other side goes drastically down, this is a resistive divider, it is automatically going to pull down the point in the middle like a lever, right. So, the fulcrum is on one side, right, this is this point is Vx, this is the fulcrum is ground. Okay. If Vx is a little higher, what we are saying is Vx is a little higher, then the output voltage on this side goes drastically down. If this goes drastically down, then because of the resistive divider, it is going to automatically bring the voltage at Vx also is going to come down. Okay. So, if it is a little higher than required, then immediately the output of the op amp is going to respond and pull it back lower. If Vx is a little lower than required, then what is going to happen? The output voltage is going to go drastically up, okay, and it is going to pull it back to the right place. So, this beam is going to be balanced right over here, all right. So, this is your negative feedback. So, this principle is called negative feedback. If the voltage over here is slightly lower than required, then the output is going to go drastically up. If it drastically goes up, then it is going to correct the mistake that happened at Vx to start with. All right. So, this principle is called negative feedback. Now, imagine a situation where the op amp was connected the wrong way. Now, what is going to happen? If Vx was slightly lower than required, now it is connected to the positive terminal, the output is going to go drastically low, right. It is going to go drastically low and it is going to pull Vx down even further. Vx was a little low, the output is going to go drastically down and then it is going to pull Vx down all the way. Okay. Then Vx goes a little further down, again the output responds by going further drastically down, right. So, this beam is not going to be balanced at all, right. You started from here, Vx was a little down, immediately the output fell drastically down. So, this is eventually going to collapse, it is going to look like this, right. If you draw a mechanical beam over there, it is just going to collapse all the way. If Vx was a little up to start with, then it is going to push up. So, the beam is going to look like this. Okay. The output is, if Vx was a little up to start with, then the output is going to be drastically up and it is going to push it upwards. All right. So, you will not get balance in this particular beam, right. This action, when the output is reinforcing the mistake, right, you started with an error, then you are reinforcing the error, this is called positive feedback as opposed to negative. Okay. If I make a mistake while teaching and you say, point out to me that you are making a mistake, right, then I will try to correct myself. If you say that no, you are doing a great job, continue, right, then I am going to make even more mistakes, right, and the more mistakes I make, you start enjoying it even more and you appreciate me even more, then I am going to make even more mistakes, right. So, the entire thing is going to go downhill. Whereas, every time I make a mistake, if you point it out and say no, this is not correct, then I will try to improve myself. All right. So, that is negative feedback, right. Negative, with the help of negative feedback, you will see negative feedback everywhere in real life, right. It is there in all places, right. Just when you are trying to pick up an object, suppose there is this object, I keep it on the table, I close my eyes and now I do not know where the object is, I am looking for it, I can't find it. Okay. The moment I open my eyes, I see where my hand is, I see where the pen is and I ask my hand to go a little bit forward by the error that I committed, I try to fix it, right. This is also negative feedback. All right. So, negative feedback is there everywhere. This circuit over here is a negative feedback circuit, all right, and here both terminals are at ground. Now, where you apply the input is irrelevant. You can apply the input, in which case it becomes this circuit. You can apply the input at the other terminal, at the plus terminal instead of over here, right. You can apply the input over here, in which case it becomes the second circuit, all right. So, both circuits come from the same root, just where you apply your input. So, I apply the input over here, I get the top one, I apply the input at this terminal, I get the second circuit, flip it around, redraw it, right. You apply input over here and redraw, right. It is just a topological, not even there is not too much topology, it is just flip the circuit and draw it again, it is the same circuit. All right, this is understood. Okay. So, let us do one more. Suppose your I do not know, do you know how to drive a car? Some of you know how to drive a car, okay. Most of you know how to drive a bike. Okay. Suppose you have a hilly road, there are ups and downs on the road, and you are told that you have to drive your bike at a constant velocity no matter what. The straight road, just that there are ups and downs all the way. Okay. You have to drive your bike at a constant speed. Now, the most important thing that you need if you are given such a task, you need a speedometer, all right, something that is going to tell you your current speed. Without a speedometer, this is a no brainer, you have to give up, you say I can't do it, all right. First thing you need, most important thing you need to do this job is a speedometer, all right. So, I am going to draw the speedometer. So, the speedometer, so I am going to call this arrow as the speed. So, this is the current speed, okay, or actually this is the current action, and the speedometer is going to measure your current action and declare a speed, a value for the speed. So, this box over here is the speedometer. All right, you have been asked to travel at a constant velocity. So, I know you have been told that this is the value 40 kmph. All right, the speedometer is always declaring the current speed. Sometimes when you are trying to go uphill, your speed is probably coming down, right. Sometimes when you are trying to go downhill, your speed is increasing, and so on and so forth. So, maybe this is 39, maybe this is 41, some number is coming out over here, okay, 38, whatever it is. Now, what is going to be your job? Your job is going to be to see that this was my target velocity, this is my current velocity, what is the difference between the two? What is the error? What error am I making? Right? Maybe I am going downhill and my speed has become 41. So, the error in that case is -1 from the target. Maybe I am going uphill, speed has become 38. So, the error in that case is +2 kmph. Fine. So, you are trying to measure the error, and then after measuring the error, what do you have to do? Depending on the error, you have to produce more action, right. Either you press your accelerator even more, or you ride your bicycle harder, right. You push more force on the pedals, whatever you want to do, right. If you are driving a scooter, you put more petrol into the engine, right. You press the accelerator, turn the accelerator in a scooter. So, this is your actuate, right. You actuate whatever is to be done, and how you actuate depends, how much you actuate depends on what is the error. If the error was 0, you do not actuate at all. If the error was -1, you have to brake. Okay. So, depending on the error, you have to actuate, you have to either accelerate or decelerate or keep your velocity just the same. just equal. Okay, so here we have a gain, usually we have a gain. All right. So, this is the general scheme of things. Now, this looks straight out of your control theory book, right. This is a classic negative feedback schematic. The op amp comes right here, right. The op amp is going to come right over here, and the job of the op amp is going to be to make sure that the two inputs are more or less equal. All right. So, in any control system you are going to use the op amp to do this job. All right. Let us go a little further. Let us I do not know what you have done in your circuits earlier circuits courses, but this would be the right time to introduce a few other circuits with op amps. Couple of popular circuits. So, you learnt you already know the inverting amplifier, the non-inverting amplifier. You can do additions, subtractions with op amps. So, for example, so what is going to happen here? If there is negative feedback, then the minus terminal will be equal to the plus terminal. That is the idea. Number 1, if there is negative feedback, minus and plus are going to be equal. If they are equal, in this case there is negative feedback. So, the voltage here is going to be 0. That means, the current in this path is V 2 by R, the current in this path is V 1 by R, and by KCL the current in the feedback path is V 1 by R plus V 2 by R. And this is the current going through the R resistor, and therefore, the drop across the R resistor, the feedback resistor, is R times the current, which means the drop across the feedback resistor is V 1 plus V 2, and you started with a voltage of 0 volts on this side. That automatically means that V out is nothing but minus V 1 minus V 2. All right, and this is generally called an adder circuit. The reason why it is called an adder is because you did the plus operation with KCL over here. Okay. So, overall there is a minus, but it's also, you could also rewrite it as minus of V 1 plus V 2. So, that is why this is called an adder. The other classic circuit is this, right, and whenever things get complicated, like in this circuit it looks a little complicated. Whenever things get complicated, you start using superposition as opposed to your traditional analysis, and superposition is going to work very well with op amps. You silence the voltage sources one by one. So, first you silence V 2, which means V 2 becomes 0 volts. Okay. If V 2 is 0 volts, then the plus terminal which is in between is also going to be 0, and then it falls back to the same old circuit. Plus terminal is at 0, I apply V 1 R, which means that V out is just going to be minus V 1. And then in the next step you silence V 1, which means you make V 1 equal to 0 and apply voltage at V 2. If I apply voltage V 2 over here, then the voltage at the plus terminal is V 2 by 2. Okay. And now it is the other circuit where I have applied V 2 by 2 at the plus terminal and I have got R to ground, R in feedback, and this has a gain of 1 plus R 2 by R 1, which is 2 in this case, 1 plus R by R. Right, we are talking about the good old circuit, this good old circuit, right. Over here I have got V 2 by 2 and I have got R and R over here. So, it has a gain of 2, and if it has a gain of 2, then the output is nothing but V 2, because V 2 by 2 through a gain of 2 becomes plus V 2. And because of superposition, these two quantities come together, add up. All right. So, this is pretty much oral analysis, you do not have to do much, right. You analyze orally, visually, you get your answer right away. Okay. So, this is called a subtractor, because it really does V 2 minus V 1. We are going to stop here and then continue in the next lecture.